look up what your radians are, or to remember your what your units are. So as we go through, pay attention to units. Because, for example, up here, so if this is in radians, and this is in seconds, your angular velocity will be in radians per second. Now you get some problems that talk about revolutions in amount of time. Revolutions is just how many times you go in a circle. You need to understand that in terms of radians. So look here, if Venus completes a rotation about its axis every 5,816 hours, what is the angular speed of the rotation of Venus in radians per second? Well, you have 816 hours. I'm going to turn that into seconds. It's going to be about 2.09. 7 seconds. And then your omega or angular speed is omega. That's what we're trying to find. So it says it makes one rotation every, so now 2.09 times 10 to the 7th seconds. So one rotation is how many radians? 5. So one rotation, your delta theta is a full 2 pi over and so you're going to end up with about 3.01. So most of the time when you're working with angular motion, you're trying to shoot for a certain set of units. Like it's easy to confuse revolutions per second, radians per second. They're very different things in terms of angular motion. So if you're looking at revolutions per second, don't set that equal to omega. Find that in radians per second. That's going to be your angular velocity. But there is a relationship between linear and angular speed. So omega is your angular speed, v is your linear speed. As long as it's covering the full distance of travel, it's your linear speed. So what you're looking at, I don't really need that. So you have an object moving around a circle. So a couple things to think about. First off, the way you would think about linear velocity is at each individual point, your linear velocity is going to be tangent to your circle. But also, as this object moves around the circle, it's going to go through a displacement. It's going to go through a displacement of s, which is our arc length. Okay, so we know that s is going to be our r delta theta. And then we think, well, average velocity and delta r is what?
Change of position.
Yeah, so starts with a d, displacement. And so in terms of an angular motion, the displacement is what?
Oh my gosh, ever.
My sister called me yesterday and she was like, what is displacement? Because she's in like physical science.
Oh,
And so like they're learning like the very generic.
yeah, it's not distance.
Yeah, she was because like one of her questions like, what's the difference between displacement and distance? Like I can tell you, Parker.
Yeah, displacement is a vector. It's a vector addition.
And then she asked me something else. I said, you think I should know?
So what we did here is now we're gonna have R delta theta, so delta T.
Yeah.
And if we separate this, so what is our, what, do you see a definition in there that you can pull out? Delta theta of what? Nope.
Yeah.
So what if we wrote it like this?
She's scared.
What is delta theta over delta T? The rate of change of your, what?
Omega.
It's not W.
W.
Well, you know what was funny last year? I can't, it's a lowercase omega, and I kept asking the class what it was. And Dawson and Sean go, we're just gonna call it the funky W.
It's W. Am I right?
No. Okay, yeah, it's omega, but
Yeah.
it's not.
Well, like it is.
Yeah. So your linear velocity at any point on the circle is going to be the radius of the circle multiplied by the angular velocity. Now, again, remember, I'm showing you how we get to these ideas. If you're ever referencing back solving problems, I always put your theorems there. So you can just kind of look back at the slide and you can see, you know, well, on my slide, they're nice pink. On the slide, on the screen, they're red. But those are your theorems that you can reference.
I have no idea what.
Okay. So now we can talk a little bit about period and frequency, uniform circular motion. So the period is going to be, you're rotating, you're going around a circle. Your period is the amount of time it takes for a singular point to go all the way around the circle.
Pi.
Now, your frequency is going to be 1 over your period. So the big capital T is your period. And then the book uses F for frequency. I don't like that. I like to go with the more traditional style with the Greek letter nu. Because, I mean, how many of you remember your basic quantum mechanics from chemistry?
I do.
You know, Planck's equation. So again, frequency. And so what we notice is eventually we get to the fact where angular speed is going to be 2 pi times the frequency. So let's think about that. If we have a velocity, we did this. So S over delta T. So displacement over time. And the time for 1 revolution around the circle is your period. This is going to give you 2 pi r times the frequency. So that's going to be your linear velocity. Then E also equals r omega. And so omega E over r. So then omega, we take this E here, is going to be 2 pi r frequency over r. So then you get to your angular speed is 2 pi times the frequency. So again, if you're looking at a circle, your frequency is how many times does your point pass the, so like you have a point on your circle that's moving. Your frequency is how many times is it going to say go all the way around in a given period of time? That's your frequency. Remember with waves, it's how many times a single point on a wave passes a certain point in a given period of time. So yes, you can actually represent wave mechanics with circular motion.
I'm laughing at, I can see your next slide.
Oh, oh yeah. So you have clothes in the dryer. Apparently this is a big deal on this campus.
Get your clothes out of the dryer.
I need to do my laundry.
One of the favorite posts I ever saw was someone posted like, so the person who stole my favorite sweatshirt in the dryer, if I see you wearing that on campus, I will in fact take you down. That was a good one.
I figured that. Oh, yeah. Remember when you posted about yourself and we all defended you?
Yeah.
I said I was going to war.
It didn't work,
I know, I was going to war.
but so let's say you have this dryer, it's spinning at 51.6 revolutions per minute. Now, see, revolutions per minute, again, you're tempted to call that the angular speed, but it's not. Now, you can have an angular speed in radians per minute. The most common way to do it is radians per second. Remember, revolutions is not radians. So one revolution is 2 pi radians. So you'd have to take that 51.6 times 2 pi to get angular velocity. If the radius of the drum is 30.5 centimeters, how fast is the outer edge of the drum moving in meters per second? Okay, so the first thing we want to talk about is your 51.6 does represent a number. 51.6 revolutions per minute. Frequency. That's actually your frequency. So, does anyone know the unit for frequency?
Hertz.
Hertz. And that is usually going to be in either revolutions per second. Now you're going to notice that when we're multiplying by like meters or something, like revolutions or radians, they're not really a unit, they're a placeholder. So another way you've seen hertz represented is either 1/seconds or inverse seconds. Because again, just like when you're using Avogadro's number, it's whatever you're looking at per second. This time it's revolutions per second. So what can we do? We want this to end up in meters per second, so I know minutes has to go away. So let's just take our 51.6 revolutions. Minute, and then in 1 minute, 60 seconds, that's going to give us, someone's popping. So now we have a frequency of 0.86 revolutions per second. Now, you can calculate an angular velocity. This will change the units to 5, so it'll be 5.4 radians per second. But you notice, but here's the thing. You see the units that we're after? So this right here, your omega, this is angular speed. Is that what we're after? No, when you see meters per second, what kind of velocity is that? Linear. So this was asking you for a linear velocity, okay? So then we know that linear velocity is r times omega.
I like it. These numbers are less.
Give it a minute.
No, I just like it more than all the letters. Makes more sense.
And this will end up giving you a linear velocity of 1.65 meters per second, which of course, if this is rotating at a constant angular speed, this linear velocity is, again, remember that velocity vector that's tangent to the curvature at any point? So if the point on the outside of the drum was to fire off at a certain point, it would fly straight off at 1.65 meters per second. We're going to get to why the point continues in a circular motion. anyone have any ideas on how that, what is it that keeps the point on a circle moving in a circle? If your linear velocity is straight off the circle at any point. Yeah, centripetal force. So we're gonna deal with that too. Okay, so rotation and translation, okay? So the axle of a wheel is gonna move, let's just say you have a wheel, you have the axle, it's gonna move a distance equal to the circumference of the wheel. Okay? So, oh no, I don't want an egg. So we're just gonna kind of take this step by step. Okay, so the first thing we know, and so we'll just say we have a point on the wheel here with a linear velocity that's a tangent to the curvature of the wheel. So that's that linear velocity we've been talking about. The axle of your wheel is going to be right in here. So you have your radius. So the way you know it's traveled the distance, first off, the way you know it's traveled the distance is the full circumference of the wheel. You have this point. You have this point on the wheel, and you imagine it's going around the wheel as the axle is moving. What we mean by the axle moving, the axle is going to have a linear velocity. Moving. So we're not talking about the axle moving in a circular motion. We are talking about thinking of the axle as a single point moving that way. Okay. Let's actually differentiate these two. We'll call this velocity center of mass. Okay, so how do you know when you've marked out a distance? So this is your beginning point, and this is your end point. And what's the equation for the circumference of a circle? Yep, 2 pi r. How do you know you've mapped out a distance of 2 pi r? Think of it in terms of the point on the wheel.
Yeah. It goes all the way around.
Yeah, so you know you've mapped out that distance when your point ends up at the same spot again.
I just forget it's on there.
I put this other one in here so that you can notice that as the wheel's going around, this point is going to hit different locations on the wheel as the wheel turns. Does that make sense why the velocity vector on the second one points the other direction? Just think about it. If the top of your wheel is moving that way, the bottom of your wheel is moving that way. What? Yeah. So you ask yourself, what is the linear velocity? What is the linear velocity of this central axis? Okay, well. So our displacement, because we're basing it off the point going around the wheel. So the displacement is going to be an arc length. It goes all the way around, so 2 pi r. The time is the period. So we also know that our angular speed r over dr equals 2 pi over t. And so the velocity of the center of mass that is going to, so we have 2 pi t r equals omega times r. So that's why I wanted to differentiate those two velocity vectors. Because you notice now that your linear velocity of the center of that circle is also your angular speed multiplied by the radius of the curvature.
I'm really blind and I can't read what the one inside the circle, what's it?
Oh, the
labeled as?
velocity there?
B what?
CM,
So
center of
it's
mass.
the
Oh,
center of
CM.
mass. So I'm differentiating between the velocity of the axle and the velocity of the point going around the tire. Okay. So let's say you have, I don't know, a cylindrical drum, barrel, whatever, and you roll it across the floor. It has a radius of 0.4 meters and makes one complete turn every 8 seconds. How long does it take to roll 36 meters? So you see, we're building up to like Newtonian kinematics using rotational motion. Okay, well. Let's think about its angular speed. Two pi over the period. Why is the period 8 seconds from the problem?
That's one whole turn.
It's the one over the frequency.
No, the period is the amount of time to make a complete revolution around a circle. So that's the 8 seconds. Okay, so this is going to give you 0.75 radians per second. The linear velocity now of the center of mass of that drum V equals omega r. That's going to give us 0.314 meters per second. Now, how do you think I figure out the distance to travel, how long it's going to take to travel that distance? Because I now have the linear velocity of the center of that drum going that way. No, what we're going to use this is the kinematic I chose just because I can make it really simple. You can solve it with another kinematic, fantastic. Because there's not going to be an acceleration. And so our delta t, the time we're looking for, and so that's going to be the full 36 meters over the velocity. And that's going to give us 114.6 seconds. See, now we're mixing and matching the rotational motion with the Newtonian kinematics. So we've covered, now we've talked about radial velocity. What do you think comes next?
Acceleration.
Radial acceleration. Okay, so the diagram here, we're going to end up demonstrating a point. Radial acceleration, so when you're moving in a circle, the acceleration you're experiencing is going to be perpendicular to the linear velocity vector at any point on the circle. And all of those acceleration vectors point towards the center of the circle, and that is called what? Centripetal acceleration. Because if you didn't have the centripetal acceleration, what would happen to a point that's trying to move in a circle? You fly off in a straight line. You have to have that centripetal acceleration pointing towards the center of the circle to even map out a circular path. I don't know, let's say we start with no, it's not quite the center of the circle. Just pretend those are at the center of the circle. So we can look at this in terms of position vectors. And so then at each one of those points, there's going to be a velocity vector that comes off. And so what can we do? So do you remember your basic equation for acceleration? Remember your basic equation for acceleration? If delta R over delta T was velocity. Acceleration. Huh?
Is it delta S?
No.
The change in R over the change in,
That's V. What is acceleration?
the change in,
Change the velocity.
the
Change in
change.
velocity. Okay, so we're looking at these as the delta V. But you notice here what we're really dealing with is velocity is a velocity vector at each individual point around the circle. So that means we're going to start thinking about this in terms of these radial vectors getting closer and closer to each other. So if you notice here, the thetas are getting much, much smaller. So this time, I have velocity like that. Like that. So if we take these two velocities, we line them up, so it's like so we can take those two velocity vectors, put them tail to tail, and what you're going to notice is your delta V is going to point like that, which shows you that your delta V at every point delta V at every point is going to point radially back into the circle. So this is where we get the concept of centripetal acceleration, because remember what we said about the direction of acceleration in delta V. If you have delta V going one direction, which way does acceleration point? In the exact same direction as delta V. So you notice your delta V is pointing radially back into the circle. Your acceleration has to be going in the same direction. And so what that gets us to is, of course, a couple ways to write this. The book uses R for radial. I think a term you've heard more is centripetal, because there's a big difference between a centripetal force and a centrifugal force. All of you who work in a lab should know what a centrifugal force is. You've all used centrifuges. So centripetal pulls back into the circle. Which way does centrifugal force send a mass? Away from the circle. But they're both radial. They're like your centripetal, centrifugal force are exactly opposite each other. And so, of course, each one of these is at a singular point. So we're looking at a your acceleration is going to be really your rate of change of your delta V. So here we get to a theorem that we can actually use. The magnitude of the radial acceleration. You have two equations you can work with. It's either the radius times the angular speed, omega squared, or it's v squared over r, which is the linear velocity squared over divided by the radius. Make sure you're keeping those two concepts separate in your head. Angular speed, linear speed. If you see a problem that says meters per second, that's linear. If you see something that says radians per second, that's angular. So as we talked about, now let's kind of look at this. Let's say if we don't draw this whole circle, I'm going to erase part of it because I want the R. I just want an arc of that circle. So let's think about we're going to have two velocity vectors. So these are going to be thinking like these right here, because the velocity vectors themselves over time will draw out an arc because they're going to start pointing in different directions. So if you take all those velocity vectors and put them tail to tail, what you'll end up forming again is another circle with all the velocity vectors pointing outwards. So pretty much the arc length that they draw out a good approximation for that is going to be delta V. And so the way you can look at this is two of your velocity vectors are going to end up drawing out an arc length with the radius of the velocity. So then, now, as you see here, your delta V doesn't really fit in the arc, but imagine those velocity vectors are getting closer and closer and closer and closer. So as that angle gets smaller and smaller and smaller, your delta V will fit right over the arc. to the point where, again, if you are looking at an infinitesimal arc length, your delta V will fit right over the top of it. Because again, think about it, the apparently unpopular opinion in 2025, but the earth is round. But you know, you still have people say, "I look out there and I see a straight line." Well, that's because the only part you're able to view of the curvature is a differential of the curvature. The difference in a derivative of a curve is a what? A tangent line. So all you're seeing, yeah, you're just seeing a differential of the curvature, which means all you're seeing is the tangent to the curve. Same idea here. Okay, so using equations we had above, we can say delta V so remember this time your radius is the magnitude of V.
Is that two mu? Or is that another V?
Oh, that's another V.
Okay.
But we also know that delta theta is omega delta T. So then we can plug this in to be V omega delta T. So then we remember that centripetal acceleration, delta V over delta T, that's going to be V omega delta T over delta T, let's see. I think I did something messed up here. Give me a second. Oh, okay. So then we're going to get V times omega. One of my V's looked like an R. That's why. But we remember from earlier that V equals R times omega, so we can put that in here. R omega times omega equals R omega squared. And you can do a very similar derivation to get the V squared over R, but when you're thinking about these, your theorems for your centripetal acceleration are going to be your either R omega squared or your V squared over R. Keep your linear and your angular speeds separate. Okay, you guys take the last 5 minutes and work on this. You should come up with a radial acceleration of 3.41 times 10 to the 4th meters per second squared.
10 to the
10 to the 4th.
Got it.
Yeah, now solve it.
I have the answer.
No, I don't care. Solve it.
Okay, now I figured it. I'm working really hard.
Remember, a lot of the stuff we cover is where these things actually come from. You can go back and reference the big equations that I put on there as your theorems. But on Monday, we are going to get to a problem you're going to work on in a group, and it's going to be a mathematical exercise because we're really going to start putting radial motion and Newtonian kinematics together. Yeah, so centripetal, radial, either A sub C or A sub R. And notice that you have a diameter in there. There you go.
What can we say?
So sometimes.
So we need to.
Just back there. Just a few slices. That's how I was so fat.
Yep, you have to convert that to meters.
So now, do we just put-
This is how I write it.
Yep.
So omega is your revolution per second.
You're looking for an acceleration in meters per second squared. Let's see here. Now, I ended up using radians because I related things through omega and then through acceleration. So if you get to radians per second, you have omega. And your acceleration is what, r omega squared?
What was the answer?
Let's see, 3.41 times 10 to the fourth meters per second squared.
I did not get that.
I appreciate the honesty.
I got 860.
It's gonna help. When I saw these, I try to relate them back through the symbolism and the equations that we're using for the chapter. That way you can kind of link things together. But know that if you get to radians per second, you have omega. And then your radius times omega squared is your acceleration.
We got to revolutions per second.
Oh, see, you're at revolutions per second. How do you get that to radians per second?
I don't know.
That's what I can remember.
So your revolutions per second is your frequency.
Oh, and in seconds, you gotta turn 7.
So one revolution is how many radians?
2 pi.
Pi radians. Yep.
Oh, no.
Your favorite snack.
Are you still playing that gambling app?
No. It's Uno.
Oh, okay. I've seen Uno destroy friendships.
I stopped gambling.
You gamble?
I used to a lot.
I've seen people save an entire hand and they do like all the like skip, pick 4, skip, pick 4. It's just.
I guess it's 45.
Wait, I got that now. Yeah,
We'll be scared.
I don't know.
Okay, so we'll continue this next week. You saw that your assignment was on the link, so.
I do that.
I got it, guys.
The assignment for this week is kinematics in a single direction. So you have a couple on there for the X direction, a couple for the Y direction.
I be doing that.